Hi, I'm Hyojin Bahng, and I'm going to talk about learning the biased representations with biased representations. And this is joint work done with Sanghyuk Chun, Sangdoo Yoon, and Seong at Clova AI, and Jaegul Choo at KAIST. So I'm going to talk about dataset bias in machine learning. Let's say our training data has most car images on the road and most frog images in the swamp. A neural network will see these patterns and use them to maximize accuracy. However, at deployment, when it sees a car in swamp or frog on road, relying on these patterns or biases in the dataset is not helpful for generalization. In other words, biases such as road and swamp are easy shortcuts to recognize car and frog. In a standard scenario, most approaches assume that training and test data have identical distributions. Therefore, relying on bias shortcuts are sufficient to achieve high accuracy. However, this assumption does not hold in the real world. We target a scenario where the training and test data have different biases. Therefore, overcoming bias is critical for good generalization. The problem is we often do not know every single bias that exists in a dataset, and it is impossible to build a perfectly unbiased data. Our approach to the cross-bias generalization problem is called rebias. Simply put, when we only give our model the original task loss, we cannot prevent it from being a biased model. To mitigate this, we characterize bias by a set of intentionally biased models, and then force our model to learn a different representation. As a result, our model becomes less biased. This raises two questions. First, how do we characterize bias with models? Second, how do we encode be different? For the first question, we will take texture bias as an example. Image-trained CNNs are biased towards texture. Thus, it maintains a very high accuracy when given texture cues, but collapses when texture cues are absent. In this case, we can build a model intentionally biased towards texture by reducing the receptive fields. An ordinary CNN has a large receptive field so that it can capture both local and global cues. By deliberately reducing the receptive fields, a model can only capture local cues like texture. Therefore, we can build a model intentionally biased towards texture by reducing the receptive fields. The second question is, how can we encode be different? We do this through statistical independence, measured with Hilbert-Schmidt independence criterion. It is the Hilbert-Schmidt norm of the cross-covariance operator in the reproducing kernel Hilbert spaces. And it is zero if and only if two variables are independent. Therefore, we minimize HSIC between the two models to supervise be different. Now we explain our objective function in detail. Given our model F and the biased model G, we denote their function spaces as capital F and G respectively. Conceptually, F completely contains G because G is architecturally constrained. We first trained a biased model by minimizing independence between the two representations F and G. In other words, G tries to catch up F while minimizing the original task loss. Then we train our model by maximizing independence between the two representations. So F tries to be different from G while minimizing the original task loss. And we repeat these steps alternatively. Eventually, G cannot catch up F due to its architectural constraint, and by being outside of the biased function space G, F is debiased. To summarize, we train F and G jointly in a minimax game, where F tries to run away from G, while G tries to catch up F. Our intention is that our model is forced to be different from multiple possible biased predictions, and therefore improve its debiased performance. Now we share our experiment results. We first validate our model by building a dataset called biased MNIST. During training, we inject color bias, where each color highly correlates with each digit. Therefore, learning color is a shortcut to achieve high accuracy, and naively trained models would be color biased. For evaluation, we measure both biased and unbiased accuracy. For the biased metric, bias is identical to the training set, and this measures the ability of the biased models to maintain a high in-distribution performance while generalizing to the unbiased setting. For the unbiased metric, colors are randomly assigned to the label so that models relying on bias would perform poorly. For the models, we set our vanilla model as an ordinary CNN that has large receptive field, and for the intentionally biased model, we deliberately reduce its receptive field to 1 by 1. It can only perceive per pixel values, so it's more liable to overfit to color. And these are the results. Vanilla F achieves 100% accuracy under the bias setting. This is how most machine learning methods are evaluated, but it does not show how much the model relies on bias for prediction. When we randomly assign colors to the label, the accuracy plummets to 33%. For the intentionally biased model, the accuracy plummets to 10%, which is random chance. This shows the case where a seemingly high-performing model has in fact overfitted to bias and does not generalize well to new situations. On the other hand, our method achieves robust generalization by learning to be different from the biased model. The accuracy boosts to 64%, and it is superior to existing debiasing methods. We further validate our model on the realistic texture bias of ImageNet. As mentioned before, ImageNet-trained CNNs are biased towards texture, so consequently models fail when texture cues are absent, and does not generalize well to unseen texture signal combinations. In this experiment, we first train our models on the subset of ImageNet containing 9 superclasses, and then for evaluation, we measure the biased metric by testing on the original ImageNet test set. Here, bias is identical to the training set and is the standard method of evaluating models, yet it is blind to the model's ability to generalize beyond bias shortcuts. For the unbiased metric, we cannot get a perfectly unbiased data. So as a proxy, we give more weight on unusual texture class combinations. We do this by getting texture clusters, and then compute accuracy for every texture class combination. So we divide number of correctly predicted samples with the total number of samples in each texture class combination, so that we upweight unusual combinations. We further evaluate our model on ImageNet A, which has challenging examples, and on ImageNet C, which measures robustness to common corruptions. For the models, we set our vanilla model as ResNet 18, which has large receptive field, and we set our intentionally biased model by substituting some of the 3x3 kernels to 1x1. Therefore, it has a small receptive field and it's liable to overfit to local texture. And these are the results. The vanilla model shows good performances on the biased accuracy, but the performance drops for the unbiased accuracy. The biased model performs worse as they are heavily biased towards texture by design. When rebias is applied to the vanilla model to make it learn cues beyond those captured by the biased model, we observe a general boost in all 4 accuracies. We finally validate our model on the action recognition task. Action datasets have been reported to have a strong bias towards static cues, so models relying on static shortcuts rather than learned temporal signals. For instance, for this opening fridge action, all the model sees is the static indoors of a fridge rather than learned a temporal action. However, there are many real-world scenarios where this static cue is absent or even correlated with a different class. In these cases, the model would fail in generalization. In this experiment, we first train our models on the kinetics dataset, which has a strong bias towards static cues. And for evaluation, we get the biased metric by testing on the original kinetics test set, and we get the unbiased metric by testing on the mimetics dataset, which has videos of a mime artist doing the same actions without context. For the models, we set our vanilla model as a 3D ResNet, which can capture both temporal and static cues. And we set our intentionally biased model as a 2D ResNet, which can only capture static cues. And these are the results. By applying ResNet on the 3D ResNet, it encourages to utilize its temporal modeling capacity by forcing it to reason differently from the 2D ResNet. Therefore, rebias improves the accuracies of both kinetics and mimetics dataset. In conclusion, cross-bias generalization is a realistic problem in deployment scenarios where models exploit bias shortcuts to recognize the target. And when bias can be characterized via models, rebias is a good candidate. Rebias effectively removes bias in biased MNIST, ImageNet classification, and action recognition. Thank you for watching.